The Earth's core just stopped spinning, and why scientists are terrified. Your maps freeze. GPS lags, then jumps. Over the South Atlantic, a satellite slips into safe mode as mission control counts radiation hits like hail on a car roof. Meanwhile, deep under your feet, the Earth's heart, its solid inner core, stops keeping pace. It taps the brakes. Some data even suggest it's drifting backward relative to the mantle we live on. If that's true, the shield that keeps your flights en route, your images from space clean, and your power steady could be wobbling at the source. To see why scientists are nervous, rewind to the first clue hidden inside earthquakes. The evidence didn't come from a lab, it came from echoes. Get this, the smoking gun wasn't a flashy instrument in orbit, it was a whisper in rock. Earthquake echoes arriving a hair earlier here, a hair later there, over decades. Today, we'll untangle 5 reveals that escalate, each one tightening the stakes. First, seismic fingerprints. We'll track time-lag twins, near-identical earthquakes taking the same path through the planet years apart, and see how their tiny mismatches betray the inner core's changing motion. Second, the tug-of-war at 3,000 kilometers down. Liquid metal swirls. A solid iron sphere tries to keep its rhythm. Electromagnetic torque pulls one way, mantle gravity tugs the other. The brake pedal? Magnetic friction that turns motion into heat, and over years reshapes the flow. Third, the field's limp. The South Atlantic anomaly is growing and splitting like a bruise. Satellites glitch, instruments reset, pilots reroute. When the dynamo stutters, the shield shows it first. Fourth, climate knock-ons. A weaker field lets more charged particles pierce the upper atmosphere, nudging ozone chemistry and polar circulation. It's not instant catastrophe, it's more volatility at the worst times. Fifth, our survival playbook. Harden the grid, bulletproof satellites, reroute flights smarter, and upgrade the forecast. There's boring work that saves everything. We're not here to hype a doomsday. We're here to connect quiet papers to loud headlines. Why Hubble drops into safe mode more often over one patch of sky, why GPS jitters during storms, why power operators watch the sun like it's a rival market. The longer the slowdown, the weaker the shield. The weaker the shield, the more our world crackles. Start with the sound the planet makes when it rings like a bell. The clues were millisecond scars on decades of seismograms. The smoking gun, earthquake echoes, and time lag twins. To understand a heart, you listen for a beat. For Earth, that beat is the P phase. Seismic waves that dive through the liquid outer core, punch across the solid inner core, and climb back out. When the same kind of earthquake takes the same route years apart, those waves should arrive in lockstep. They don't, and that tiny drift is the tell. The heroes of this story are doublets, near-repeat quakes from places like the South Sandwich Islands. Picture 2 quakes along the same fault, similar size, similar path, separated by years. Seismologists stack their signals and go hunting for a few thousandths of a second in difference. It's absurdly small, coffee spill small. But when a planet's core changes speed relative to the mantle, that's where it leaks through. Here's the stakes. If the inner core speeds up or slows down relative to the crust, the anisotropic iron crystals inside, those that preferentially pass waves faster in certain directions, rotate with it. The path stays the same, but the texture the waves cross has turned a little. The phase arrivals drift. On paper, it's a wiggle. In reality, it's a global metronome, phasing with itself. Action. In the 1990s and 2000s, travel times of Pk compared to later core phases showed a pattern. The inner core seemed to be super rotating, slightly outrunning the mantle. Then the drift eased. Since around 2009, multiple teams noticed the differences narrowing, even reversing sign in some pairings. In 2023, Song and Yang, Nature Geoscience, argued the inner core was slowing relative to the surface and heading into a downswing of a decades-long oscillation. In 2024, a broader waveform study in Nature added fresh doublets through 2023 and found backtracking, a reversal relative to the mantle, at a rate around 0.05 to 0.15 degrees per year. That isn't a literal stop, it's a change in the lead lag between 2 nested spheres. Impact. Those numbers mean the inner core's orientation, as felt by seismic waves, is shifting on human timescales. It suggests a natural multi-decade cycle, not a one-way crash. But when the cycle hits a slowdown, the forces coupling the core and mantle, the very ones that steer the geodynamo, are also rebalancing. That's where the surface consequences may emerge first, not as earthquakes or volcanoes, but as quirks in the magnetic shield. Meanwhile, something else was happening. Independent methods started lining up. Normal modes, the planet's free ring after giant quakes, hinted at similar rotation rates. Coda waves that scatter inside the core showed consistent changes. Inner core backscattered waves, a hard-to-catch reflection from deep inside, pointed the same direction. When different techniques with different biases converge, scientists take notice. The evidence isn't one instrument with one idea, it's a chorus. What nobody knew at the time was whether the slowdown was a kink or a rhythm. Some teams suggested a 70-year oscillation, consistent with Song and Yang 2023, with alternating decades where the inner core leads, then lags. Others argued for shorter cycles, 20 to 30 years, based on different stacks and statistical windows. The debates got sharp because the shifts we're measuring are so small that how you pick, filter, and align the waveforms can tilt the answer. But the broad shape held. The mid-2000s were a pivot. The 2010s showed a deceleration relative to the mantle. The early 2020s added evidence for backtracking. Here's the human moment. A researcher at a northern array pulls up a new South Sandwich doublet. Two traces look like carbon copies. Then the cursor nudges 0.02 seconds. That's it, a breath. But it's consistent with 5 other paths from the same region and nearly a dozen new events. She leans back, realizing those 2 lines are the sound of the planet's core slipping phases with the surface we live on. But there was one problem. A change in arrival time could, in theory, come from something else, like evolving anisotropy, a rearrangement of crystals without bulk rotation change, or subtle variations in the outer core flow that bend paths. That's why the teams didn't rely on a single kind of wave. They cross-checked PK-IKP against other core-sensitive arrivals and looked for coherent waveform distortions, not just first clicks. They tracked antipodal stations, used arrays in Alaska and Canada, and kept adding fresh doublets as new quakes happened. The pattern persisted across methods and instruments. This was the moment everything changed. When the waveform studies through 2023 extended the timeline and still saw the same directional pivot, it turned a possibility into a trend. If the inner core is indeed in the downswing of an oscillation, then electromagnetic coupling between the liquid metal flows and the solid core must be redistributing torque. That can tweak the geodynamo, the chaotic dance that builds our magnetic field. In the aftermath, attention turned upward. If the inner engine is changing rhythm, the magnetic field should respond with subtle but trackable signatures. Shifting flux patches under Africa and South America, more turbulence in the South Atlantic anomaly, and a continued long-term dipole weakening. None of that proves cause and effect by itself, but when the heartbeat slips and the shield stutters, you don't ignore the coincidence, you test it. To understand why the inner world might be tapping the brakes now, we need to leave the seismograms and dive into the coupling zone, where metal flows grab iron, field lines twist, and continents above quietly push back. Because if the echoes were the message, the torque is the hand that wrote it. The tug-of-war core mantle coupling and magnetic friction. Start where the echoes point, at the boundary between the inner and outer worlds. Microstory. A modeler in Boulder runs 2 core flow simulations side by side. She tweaks one parameter, a slight change in electromagnetic coupling strength at the inner core boundary. In one run, flux patches under Africa hold. In the other, they shear and drift west faster. Same heat, same chemistry, just a different clutch setting. Her takeaway is simple. A tiny torque change deep down can redraw the magnetic map we live under. The inner core is a hot, solid iron nickel sphere. Around it, the outer core is a roiling ocean of liquid metal, moving in loops and jets that generate the magnetic field. Above that, the mantle is sluggish rock, but it's heavy enough to matter. None of these layers spin in perfect lockstep. They negotiate, they tug, they compromise. Here are the stakes. If the torque balance shifts, if magnetic grip strengthens or weakens, if mantle gravity leans harder, then the inner core's lead or lag changes, and the geodynamo's geometry tilts with it. That means where magnetic field lines emerge and dive can drift, wobble, or fray. The consequences are quiet for a while. Then satellites start logging errors. Auroras spread to strange latitudes, and power operators get nervous. Action. Inside the outer core, convective flow twists magnetic field lines into spirals. Those lines thread the solid inner core. Because iron conducts, the changing field induces currents in the inner core, and those currents feel a torque, electromagnetic coupling. Think of it as a magnetic clutch. When the outer core flow tries to drag the inner core along, the clutch engages. Meanwhile, the mantle's uneven. Gravity, shaped by deep structure in the continent's mass above, tries to align the inner core a certain way. That's gravitational coupling. Add in the fact that the inner core's surface isn't smooth, it's lumpy topography. Fluid shears across those bumps create viscous and pressure torques, 3 hands on one wheel. What nobody knew for sure until the slow pivot showed up in waveforms was which hand was tightening. Multi-decade oscillations have been proposed. Flows reorganize. The magnetic clutch tugs the inner core forward for a spell. Then the mantle's gravitational alignment and core mantle boundary heat flow asymmetries push back. The result is a swing, lead, then lag on timescales of decades. A slowdown in the 201s fits a downswing of that pendulum. Impact. When electromagnetic coupling dominates, more rotational energy moves into the fluid, stirring the dynamo differently. That changes the distribution of flux patches, regions where field lines are concentrated at the top of the core. The African and South American patches that underlie the South Atlantic anomaly become especially important. If those patches weaken, drift, or split, the field above thins. A subtle torque change deep below becomes a radiation map in orbit. Meanwhile, something else was happening near the boundary. Heat leaving the core into the mantle isn't uniform. Where the lowermost mantle is hot and sluggish, less heat escapes. Where it's cooler and dense, more heat siphons out. That pattern sets the lanes for outer core convection. Large-scale mantle features, like the African and Pacific superplumes, may gate where fluid rises and falls, and therefore where magnetic field is generated strongly or weakly. In other words, continents and deep mantle structures don't just sit there, they steer the dynamo by shaping the heat budget. But there was one problem. Friction. Not the sandpaper kind, magnetic friction. When field lines connect a moving fluid to a solid conductor, they can convert differential motion into heat. It's tiny, but over years it matters. Think of bumper cars at 5,000 kilometers down, except the cars are molten iron and the bumpers are magnetic springs. Every jostle damps a bit of relative motion. In a downswing, that damping can help the inner core lose its lead and drift into lag. Action on the mantle side, tides, topography, and slow continental drift. Earth tides flex the whole planet by centimeters daily. At the core mantle boundary, those periodic stresses can modulate flow and pressure, altering the torque environment. Mantle mountains at the boundary, kilometers of relief frozen into deep rock, shape how fluid scrapes past, changing shear and drag. Even the redistribution of mass by supercontinents over millions of years leaves long-lived fingerprints on the torque balance. On human timescales, that's not shifting fast, but it sets the baseline the magnetic clutch works against. Stakes again, concrete this time. If torque redistribution is nudging the dynamo into a less stable geometry, you expect signals. Faster westward drift of flux lobes, growth and splitting of weak field regions, more jerky secular variation. That's what observatories and satellites have been reporting. It's not proof that the inner core slowdown caused it. Both could be responding to the same deep reorganization. But from a risk perspective, causation is less urgent than correlation that persists. Here's where it gets tricky. The inner core itself isn't a uniform ball. Its iron crystals have preferred orientations that can evolve as new solid iron freezes onto its surface from the outer core, inner core growth. There's evidence for a snow zone at the top of the inner core, slushy crystallites that settle like metallic snow. That slurry can change how torque is transmitted, acting like a seasonal slick on the clutch. If the snow layer thickens or thins with changing heat flow, coupling strength shifts. Now your pendulum has a moving pivot. Micro story. In Paris, a lab team stirs a tank of salty water over a rough sphere to mimic shear across a bumpy boundary. Add a thin gelatin layer to imitate snow, and the drag drops. Remove it, and the flow bites harder. The plots on the wall aren't the core, but the pattern is universal. A thin layer can flip how a system transmits force. Impact, immediate and practical. A slightly weakened coupling that lets the inner core lag a bit more can redirect where field lines bundle at the core mantle boundary. The surface field then trends weaker in those regions, and satellites crossing overhead take more hits. Airline operators see higher radio noise on polar routes during solar storms. Grid planners model larger geomagnetically induced currents for the same solar wind input. The machine still runs, but the tolerances slip. So, the tug-of-war isn't a single rope with two teams. It's a braided mess. Electromagnetic clutch, gravitational alignment, viscous drag over a lumpy boundary, heat flow, patterning, and a snow-dusted inner core surface, all adjusting at once. The seismic pivot told us the balance changed. The field's behavior hints at where it's going. If the dynamo is stuttering, the magnetic shield will show it first, and it already is. Symptom number 1, the South Atlantic anomaly isn't waiting. While torque shifted in the deep, a bruise spread across the sky. The South Atlantic anomaly, SAA for short, sits over Brazil, the South Atlantic, and nudges into southern Africa. To a satellite operator, it's a no-fly zone you can't avoid. Pass through, and your instruments face a rain of energetic particles that the magnetic field would normally deflect. Memory bits flip, star trackers lose the sky. Sometimes the whole spacecraft slips into safe mode to ride it out. Here are the stakes. The weaker the field over this patch, the deeper the inner edge of the radiation belts dips. That puts the flow of charged particles right in the altitude lanes, where Earth observation and science satellites live. The difference is measured in glitches and resets. On the surface, it's easy to shrug at a quiet region of magnetism. In orbit, it's the one corridor you plan around every single day. Action. Over the last decades, maps from missions like Orsted, CHAMP, SWARM, and ground observatories have watched the SAA expand and drift west. Within the broader oval, smaller hotspots form and merge cores of even lower intensity. Think of it like an eddy splitting off a current and then rejoining downstream. Operators learn the rhythm. Schedule software uploads outside the SAA window, harden the most sensitive electronics, add error-correcting memory that can tolerate cosmic confetti. Hubble's ops team built their calendar around it. They suspend observations while crossing the anomaly because the risk of detector hits is simply higher. Meanwhile, something else was happening beneath the map. Their sat lines up with weak field flux patches at the top of the core under Africa and South America. Core flow models show these patches drifting and reshaping, which helps explain why the anomaly migrates and splits. That fits our torque story. If the deep engine's geometry is shifting, the top of core pattern should move, and the surface field responds. You don't need a full reversal to complicate spaceflight. You just need a persistent thin spot that keeps thinning. Impact, immediate, and mundane. Satellites crossing the SAA report spikes in single event upsets, SEUs, where a single particle flips a bit in memory. Most are corrected, some aren't. That's when you see safe modes, system reboots, and occasional instrument restarts. The European Space Agency and NOAA bake SAA statistics into risk estimates for their fleets. Commercial operators do the same. For crewed missions, dose adds up. It's not just one pass, it's thousands over a career. Flight surgeons track it like they track hours in high latitudes. Airlines feel it at the edges. At cruising altitude, you're still under the bulk of the atmosphere. But during strong solar events, the extra ionization over weak field regions can add noise to high-frequency radio and marginally bump radiation doses on long-haul routes. Most days it's trivial. On the wrong day, with the sun flaring, dispatchers reroute and pilots use alternate comm bands. Every detour costs fuel and time. Multiply by a fleet and a year, and it's a line item. What nobody knew in the early anomaly maps was whether this was a phase or a path. The trend says path. The dipole, the global bar magnet part of the field, has been weakening since the 19th century, and the SAA rides that decline. The anomaly's westward drift matches the westward drift of flux lobes we track globally. And inside the SAA, those hotspots that come and go, they're telling us the core's flow isn't smooth. It's reconfiguring in steps. Here's a micro story. A satellite engineer in Darmstadt watches telemetry tick to red as their spacecraft enters the SAA. The onboard computer logs a burst of corrected errors, then one that isn't. Safe mode. Cameras close, reaction wheels idle, pointing goes soft. 20 minutes later, after exiting the anomaly, they coax it back to life. It's routine. It's also an invoice. Lost science time, ground station minutes, fatigue for a team that now expects the bruise to push a little farther west next year. But there was one problem. The anomaly is a symptom, not a diagnosis. Weak field could come from any combo of deep changes. Flux patch drift, core flow accelerations, or a subtle change in coupling at the inner core. We can't point from the SAA to a single cause. What we can do is measure its growth, tie it to the broader secular variation, and plan for more of it. The SAA isn't waiting for a headline about reversals. It follows the physics. If the dynamo's geometry keeps sliding toward less stable patterns, the bruise will deepen, and every orbit that crosses it will pay a toll. Symptom number 2, a field that's bleeding.
Strength. While the SAA makes headlines, the background story is the slow fade of the whole shield. Since the 1800s, observatories have watched Earth's magnetic dipole, think the bar magnet part of the field, lose strength. It's not a collapse, it's a steady leak. The numbers aren't abstract to the people who map them. Every decade, the contour lines shuffle. Instruments that once agreed need recalibration. The compass still points north, but that north is less bossy than it used to be. Here are the stakes. A weaker dipole means more solar and cosmic particles can thread the upper atmosphere, especially during storms. It also means the field gets patchier, with regional highs and lows that shift faster than maps can age. Navigation systems lean more on models. Satellites face a noisier sky more often, and when the sun shoves, the ground pushes back. In power lines, in pipelines, in rails, through currents that weren't there before. Action. The field isn't a static dome. It's a living pattern of flux lobes, bundles of field lines that drift westward like weather systems. For 2 centuries, that westward drift has been a quiet metronome, measured first by ships and compasses, then by satellites like Ørsted, Champ, and Swarm. As the lobes slide, they reshape where the field is strongest and weakest at the surface. Pair that motion with the dipole decline, and you get a map that looks more restless every year. Meanwhile, something else was happening deep below. Core flow models that assimilate satellite data show jets and gyres at the top of the outer core speeding, slowing, and sometimes reversing lanes. Those changes line up with shifts in flux patches beneath Africa and South America, the same underpinnings that feed the SAA. It suggests the dynamo is in a reconfiguration phase. Not broken, not calm, just moving furniture in a cramped room. When furniture moves, toes get stubbed. Impact. The scary part isn't that compasses will go haywire tomorrow, it's that instability rides with weakening. A thinner shield feels storms more. During a strong coronal mass ejection, more energy can couple into the magnetosphere and ionosphere, amplifying geomagnetically induced currents at the surface. Power grids see reactive power swings, transformers heat up from stray harmonics, and protections designed for yesterday's storms run out of margin. Quebec, 1989, wasn't the biggest storm imaginable. It was big enough with a stronger field than today's. GPS doesn't want to cosplay as a treasure map from 1702. But under a wavier ionosphere, stirred by solar ultraviolet, particle precipitation, and the field's own changes, signals refract and delay unevenly. That injects errors that need real-time corrections. Aviation, precision farming, drilling, they all bought accuracy on the assumption that corrections would keep up. They do, mostly. During storm peaks, mostly turns into call your backup. Pipelines learn the hard way. Indigenous to their business is cathodic protection. Small currents that keep steel from corroding. Geomagnetic storms induce currents that ride those same lines, flipping protection on its head and accelerating corrosion in the wrong spots. Operators have monitors, but a field that's bleeding strength means more days per cycle, where the induced current budget gets tight. Maintenance moves up the calendar. What nobody knew for sure was how much the inner core's rhythm mattered to this bleed. The geodynamo is mostly an outer core show, driven by heat and composition. But flux lobe behavior hints at deeper influence. If the inner core's lag alters how field lines anchor and slip, the outer core's flow responds, and the secular variation, the slow drift of the field, picks up new quirks. You don't need a grand reversal to get messy maps. You need a slightly different clutch setting for a decade. Here's a micro story. A grid operator in Northern Europe runs a storm drill. The inputs look routine, another solar wind stream from a coronal hole, but the model flags higher induced currents than the last time a similar stream hit. He checks the KP forecast again. Same. The difference isn't the sun, it's the ground's magnetic stiffness trending looser. He calls for extra reactive reserves anyway. Later, during the real event, the alarms stay quiet. It's not drama, it's prudence, informed by a field that gives up a little more each year. But there was one problem. Decline isn't destiny. The field waxes and wanes over centuries. Paleomagnetic records show long recoveries after slumps. The concern now isn't a mythical instant flip.
It's the convergence of weaker baseline, rising tech dependence, and a solar cycle heading toward peaks that repeat whether we're ready or not. A field that's bleeding strength doesn't guarantee disaster. It guarantees that the next punch lands harder.
The climate link. Space weather, ozone, and atmospheric chemistry. While the maps dimmed and the grids braced, the atmosphere started to whisper back. A weaker magnetic field isn't just a tech problem. It changes who reaches the sky. Charged particles that would have been steered away thread deeper into the upper atmosphere, especially near the poles and over weak field corridors. They don't burn the air, they tweak it. Chemistry first, weather later. Microstory. A researcher in Helsinki watches the auroral cameras glow after a storm, then opens ozone profiles from the same night, a clean dip over the polar cap. 3 days later, reanalysis maps show the stratosphere a couple of kelvins cooler. It's not a blockbuster, but the timing lines up. She adds a note to the forecast brief. Space weather injection likely nudging the vortex this week. Here are the stakes. Ozone isn't just sunscreen. It shapes temperature gradients in the stratosphere, and those gradients steer the polar vortex like rains. Nudge ozone in the wrong season and jet streams shift. Storm tracks wander. At the surface, you don't feel ozone loss. You feel February acting like April, or a blocking high that refuses to move and turns a wet week into a flood month. Action. During geomagnetic storms, energetic particles, electrons and protons, spiral down magnetic field lines and collide with nitrogen and oxygen in the mesosphere and stratosphere. Those collisions generate odd nitrogen and odd hydrogen compounds, NOx and HOx, that catalyze ozone destruction, especially in polar night when sunlight can't repair the loss. Satellite instruments have watched these pulses. A storm hits, particle precipitation spikes, NOx surges, ozone dips for days to weeks. Add a weaker magnetic shield, and the same solar event pushes more particles farther, longer. Meanwhile, something else was happening higher up. The thermosphere puffs during storms as energy pours in. That expansion increases drag on low Earth orbit satellites, but it also stirs the ionosphere, the charged layer that bends radio waves. Disturbed ionosphere means shifty GPS delays and noisier high-frequency comms. That's not climate, but it's the same doorway, more energy coupling from space into air. Over many events, the average state shifts. What nobody knew for sure was how much these space weather jolts matter next to greenhouse gases and aerosols. The honest answer: greenhouse gases dominate long-term warming. But particle precipitation is a credible modulator on seasonal scales in high latitudes. Studies have linked strong solar proton events to short-lived ozone losses and to changes in stratospheric temperatures that propagate downward, nudging the North Atlantic Oscillation and the Southern Annular Mode. The signal is subtle, not cinematic, yet timing matters. If a storm hits when the polar vortex is already wobbly, the nudge can tip it. Here's where the sun's calendar meets ours. Solar cycles run roughly 11 years. During maxima, flares and coronal mass ejections are more common. If that maximum arrives while the dipole is weaker and the SAA broader, the same burst of particles finds less resistance. The cumulative effect isn't apocalyptic. It's more frequent disruptions to the chemistry that sets the stratosphere's thermostat. Think of it as adding static to a radio that's already poorly tuned by other forces. Action in the chemistry lab. NOx, produced near 80 to 100 kilometers, can descend into the stratosphere during polar night, sustained by the vortex's cold hold. There, it accelerates ozone loss through catalytic cycles. HOx acts faster, but fades quicker. Observations from satellites like Aura and ground-based LiDARs corroborate this dance. After major storms, scientists see fingerprints, dips in ozone columns, cool spots aloft, slight pressure shifts. Models translate those into altered wave propagation that can influence surface patterns weeks later. Impact on the ground. In some winters, polar cap cooling aloft strengthens the vortex, tightening the jet and corralling storms differently over North America and Europe. In others, the energy input perturbs the wave-mean flow balance, encouraging sudden stratospheric warmings that split the vortex and dump Arctic air south. No single storm calls to play. The ensemble does. A weaker field increases the odds that any given solar shove matters. Clouds add a speculative edge. Ionization can seed ultrafine aerosols,
that under the right conditions grow into cloud condensation nuclei. Some studies suggest small effects on low cloud cover at high latitudes during strong particle precipitation events. Others find little to no robust signal once you factor out confounders. The takeaway isn't space weather controls clouds. It's that ionization is one more knob on a mixing board already filled with greenhouse gases, sea surface temperatures, and land feedbacks. The knob is small. In a noisy song, small knobs can still shape a bar. Here's a
Micro story. A forecaster in Tromsø watches a model run after a midwinter solar storm. The stratosphere over the pole is a few kelvins cooler than last week. Ozone columns dipped. The jet angles differently into Scandinavia. She nudges the probability for a blocking ridge. Not because of the sun alone, but because space weather just loaded the dice that the North Atlantic pattern would flip. 3 days later, storm track shifts south. The headlines talk about a surprise. She shrugs. It was in the chemistry. But there was one problem. Attribution is tricky. You can't tag a flood to a glancing blow from a coronal mass ejection without overpromising. The safer frame is risk. A weaker magnetic field is a vulnerability multiplier. It lets more space weather reach the layers that decide how ozone, winds, and waves talk to each other. Layer that on top of a warming world, and you get more volatility, not a single new direction. Stakes. Recentered. This isn't instant apocalypse. It's a nudge toward more extremes and more odd timing. Late thaws, early snaps, rain where you counted on snow. And it dovetails with the tech story. The same storms that tweak ozone also scramble comms and swell the upper air. When the sun swings and the shield sags, our electronics and our weather models get tested on the same day. Tech fragility, grids, satellites, and the quiet panic. Here's where the abstract turns into invoices. When the field thins and storms run hot, our machines take the punch first. The quiet panic isn't people screaming. It's engineers building workaround after workaround and hoping the next hit lands on a weekend. Start above the atmosphere. Satellites live in a shooting gallery, and every orbit is a bet. Single event upsets, microscopic particle strikes, flip bits in memory and logic. Most days, error-correcting codes catch them. On SAA crossings and during storms, counts climb. Star trackers pepper with bright pixels and drop lock. GPS receivers on orbit glitch. Attitude control burns propellant to recover pointing. The software learns to duck, disable sensitive instruments in danger zones, schedule reboots after high-dose passes, cache commands in duplicate. None of that produces headlines. It just quietly eats mission life. Meanwhile, the atmosphere breathes harder. A strong geomagnetic storm pumps energy into the thermosphere. Density climbs a few percent to tens of percent at low Earth orbit. Drag increases. Orbits decay faster. Constellations need extra maneuvers to hold their lanes. If you plan fuel for 5 years and the sun throws 2 bad seasons, your margin shrinks. Debris swarms respond too, sinking into busier altitudes and raising collision risk. Operators coordinate avoidance like air traffic control in a fog. Here's a micro story. A CubeSat team in New Zealand budgets propellant to maintain altitude through the year. 2 storms later, their orbit has dropped more than expected. They spend fuel to climb. Another storm hits. The spreadsheet's comfort buffer is gone. Their mission still works, but the end-of-life date just stepped closer. No drama, just a shorter timeline. Now drop to 60 degrees latitude where ground systems feel the current. When solar wind couples into our magnetosphere, it sets up electric fields over continents. Those fields drive geomagnetically induced currents, GICs, through long conductors, power lines, rails, pipelines. In a grid, GICs sneak in on transformer neutrals, saturate the iron cores, and push devices toward heating and harmonics they weren't built to love. Protective relays trip lines to save equipment, voltage sags, operators scramble reactive power to prop the system up. Most days, nothing breaks. On a bad day, contingencies stack. Quebec 1989 is the cautionary tale. A storm pushed GICs that tripped lines, cascading into a province-scale blackout in 90 seconds. Transformers as far away as New Jersey took damage that took months to repair. That was with a stronger global field than today's. Modern grids are bigger, more interdependent, and in some places, more constrained on reactive reserve. The good news, utilities learned. The bad news, physics doesn't care about lessons. It cares about impedance and geography. Action behind the scenes. Grid operators watch space weather like they watch demand curves. Forecast desks parse solar wind speeds, IMF orientation, and KP indices.
When a storm threatens, they postpone maintenance, bring extra spinning reserve online, redistribute load flows, and lower thresholds for alarms. Some lines get series capacitors to block DC like JICs. Some transformers get neutral blocking devices. Monitoring expands. Magnetometers by substations, GIC meters on neutral leads, thermal sensors on hotspots. It's not glamorous, but it's why lights stay on. Pipelines fight a different battle. They push small protective currents to keep steel from corroding. GICs ride along those same paths, reversing protection or overcooking the system.
Over time, the wrong sign on a stormy week means a weld joint ages faster. Operators track it. Dig crews replace sections on a schedule colored by solar seasons. Again, no screaming, just budgets. Aviation lives in the overlap. Polar routes cut time, but they run under open magnetic funnels. On quiet days, comms are fine and doses are modest. During proton events and disturbed ionospheres, high-frequency radio gets noisy or goes quiet. Planes detour to mid-latitudes, burning more fuel. Dispatchers weigh headwinds against blackout risks. Flight crews track cumulative radiation like miners track dust. It's industrial hygiene with a space weather accent. Subsea cables dodged the worst last century because repeaters broke long conductors into segments. But the landing stations and long terrestrial backhauls that stitch continents to cities are vulnerable to GICs. As traffic grows and redundancy tightens, a storm that coincides with terrestrial grid stress can make network operations twitch. Engineers add surge protection, diversify paths, and simulate worst-case outages. The threat isn't a single kill shot. It's a multi-system nudge that exposes brittle joints. Space is basically throwing popcorn at our electronics, except the kernels are tiny bullets. So designers toughen the bowl. Radiation-hardened chips trade speed for resilience. Triple modular redundancy votes out bad bits. Watchdog timers yank processors back from lockups. Safe mode logic gets SAA aware. Constellation operators adjust duty cycles around anomalies. Insurance underwriters price all of this, and premiums quietly reflect a field that bleeds strength. Here's the part nobody likes to say out loud. Our mitigation playbook assumes yesterday's baseline. As the dipole declines and anomalies grow, the same storm delivers more dose, more drag, more current. That doesn't mean disaster is inevitable. It means margins shrink if we don't add new ones. Now fold the human factor back in. Satellite controllers schedule sleep around storm windows. Grid operators hold calls at 3 a.m. when instruments twitch. Airline dispatchers move metal because the polar cap ionosphere burped. None of it makes the evening news. It's the quiet panic of professionals who know the sun only has to get lucky once on a weak field day. So the question isn't whether we can cope. We can. It's whether we'll harden ahead of the curve. Because if the inner engine keeps tapping the brakes and the shield keeps thinning, the machines we rely on will be the first to tell us, with resets, reroutes, and relay clicks. Reversals versus excursions, what history actually shows. You're probably yelling the question, does a slowing inner core mean the poles are about to flip? To answer it, we have to leave the dashboards and walk into deep time, where rocks keep score better than headlines. Here are the stakes. A full geomagnetic reversal is not a light switch. It's a long, messy transition that weakens the shield for centuries to millennia. Life survives. Technology, if it existed, would struggle. An excursion, by contrast, is a short, sharp detour. The field collapses, directions wander or briefly flip, then the system snaps back within a few thousand years or less. For us, a prolonged, weak field without a clean, completed flip could be the worst combo. Maximum radiation and instability, minimum certainty. Action. Start with the Brunas, Matayama reversal, about 780,000 years ago. Lava flows cooled across the world record a wholesale swap. Compasses that would have pointed north then point south now. But the change wasn't overnight. Paleomagnetic stacks show a chaotic interval where the dipole strength plunged to a fraction of today's value. Directions wandered, and non-dipole features, regional quirks, ruled the map. The process likely took thousands of years. If you were a migratory bird, you'd still find home using the sky and landmarks. If you were running a satellite constellation, you'd be filing insurance claims. Meanwhile, something else was happening in shorter pulses. The Longchamp excursion, around 41 to 42,000 years ago, was a quick dive. The dipole collapsed to roughly 10 to 20% of its usual muscle. Magnetic direction shot off course for a few centuries. Then the field recovered. We didn't have satellites, but we do have isotopes. Tree rings and ice cores captured spikes in radiocarbon and beryllium-10 production, cosmic rays leaving bigger fingerprints when the shield thinned.
Archaeological layers suggest auroras at odd latitudes. It wasn't the end of the world. It was a world under harsher space weather. The Mono Lake excursion, roughly 34,000 years ago, tells a similar story of sudden weakening and directional whimsy followed by recovery. Each excursion comes with a pattern. Isotopes up, dipole down, directions wandering, then a restabilized field. The lengths vary, but the lesson sticks. The geodynamo likes to meander. It only sometimes commits to a full swap. What nobody knew for sure, still don't, honestly, is how the inner core behaved during those episodes. We can't replay its motion directly, but models suggest that changes in coupling and core flow geometry can push the system into states where the dipole slumps and higher order components dominate. That's the look of an excursion. Messy, multipolar fields splashed across the globe. A full reversal might need deeper reorganization, with the dipole re-emerging opposite in sign after the turbulence. Here's the bridge to now. The inner core's recent backtracking is measured in tenths of a degree per year, part of a likely multi-decade oscillation. That is not the signature of an imminent flip, but it is a sign that the torque environment is changing, and torque matters for the geodynamo's architecture. Pair that with a centuries-long dipole decline and a South Atlantic anomaly that keeps sprawling, and the likelier near-term scenario isn't a dramatic reversal, it's a drawn-out, weak field phase with regional chaos. Impact. For technology, excursions, and protracted slumps are brutal. Frequent geomagnetic storms couple more energy into the system. Satellites take more radiation hits and more drag. Grids see stronger induced currents for the same solar inputs. GPS corrections work harder over a jumpier ionosphere. Aviation racks up more reroutes. Pipelines accelerate maintenance cycles. None of this requires poles to swap. It just needs a field that spends decades underperforming. For climate couplings, a weaker field means more particle precipitation on average, especially in polar caps and over weak field corridors. That's more NOx injections into the upper atmosphere during maxima, more short-lived ozone dents, and more chances to nudge circulation when the timing lines up. It's still subtle compared to greenhouse forcing, but subtle can steer seasons when the background is primed. Here's a micro story from geology. A volcanologist chips a fresh flow in the Auvergne, France. The compass points the wrong way in the lab. The rock froze during Bruna's Matayama chaos, its iron grains locking in a sky where North wasn't in charge. At the same time, across the planet, a pine tree grew slightly different rings as radiocarbon production ticked up. Those tiny records, stitched across continents, are our time machine. They tell us the field can wobble hard, then recover, and it has done so again and again. But there was one problem with the flip narrative. It sells drama that the data don't guarantee. Reversals are rare on human timescales. Excursions are more common. The current signals, inner core, deceleration, dipole decline, the SAA's spread, fit a story of instability without a mandated flip. That's arguably tougher for modern life because it stretches risk across careers, budgets, and infrastructure lifetimes. So where does this leave us? With priorities. We focus on the hazards that don't need a reversal to bite. We watch isotope proxies for context, field maps for trend, and seismic echoes for the engine's rhythm. We plan as if the next decades bring a weaker, twitchier shield. If the poles eventually trade places, we'll see it coming in centuries of warning. Our problem is the long dip before any switch. The timeline, decades, not centuries, for the next phase. While deep time offers comfort, the next chapter runs on our clocks. The signs we've traced, inner core, backtracking, dipole decline, the SAA's sprawl, point to a phase measured in decades. That's close enough to change budgets, standards, and the way we schedule risk. Start at the early 200s pivot. Seismic doublets suggest the inner core's lead began shrinking around then, sliding toward today's lag. In the same window, magnetic maps showed the SAA accelerating its westward drift and berthing sub-lows inside the main dent. By the 201s, satellite operators treated the anomaly as a permanent operation constraint, not a quirk. The lines on both graphs, echo, timing, and field intensity, kept bending. Near term, the forecast isn't mysterious, it's momentum. Expect the SAA to keep broadening and splitting over the next 10 years, with the main minimum inching farther west and nudging deeper at satellite altitudes. That means higher error rates for spacecraft crossing the corridor, more conservative safing rules, and shorter instrument duty cycles on vulnerable payloads. Leo drag spikes will track the solar cycle. During the current maximum and the next, storms will puff the atmosphere, trimming months off lifetimes if margins weren't generous. Constellations will plan extra station keeping, and debris avoidance windows will get busier when density swells. On the ground, grids will treat moderate storms like notable events. With a thinner baseline field, the same solar wind couples more energy. Utilities in mid-latitudes will rehearse Quebec 1989 playbooks more often, pull maintenance windows off storm days, and pre-stage reactive power. Expect a handful of regional
disturbances each cycle. Brownouts avoided by tight margins. A few transformers that run hotter than planners like, and post-event reports that read, "We were close." Insurance actuaries will quietly update tail risk assumptions. Aviation's timeline is recurring chores with occasional spikes. Over the next decade, polar route detours during proton events will add fuel burn and crew logistics costs. Not weekly, but often enough to matter. Dose monitoring will become routine across fleets, not just a checkbox for long-haul crews. HFCOM blackouts will remain episodic, pushing planes onto SATCOM and alternate procedures that airlines will test every season like fire drills. The industry will bake space weather waypoints into dispatch tools the way wind and turbulence already are. Medium term, 2 to 3 decades, the global dipole slide shows up in everyday models. World magnetic model updates will tighten cadence. Consumer devices won't notice, but surveyors, drillers, and nav systems tied to magnetic references will refresh more often. We'll likely see measurable percentage declines in field strength across broad regions. Not dramatic, but enough that storm thresholds for operations step downward. Regulators will codify GIC monitoring. New transformers will arrive with higher thermal margins by default. Series capacitors will spread from high-latitude lines to mid-latitude corridors, and neutral blocking devices will move from pilot projects to standards in vulnerable geologies. Satellites built in that window will assume a rowdier sky. Radiation-hardened parts get a bigger share of procurement. Error-correcting memory becomes ubiquitous, even on small sats. Mission concepts factor SAA crossings into science yield from day one. You'll see storm modes advertised in spec sheets, like cars brag about traction control. Constellation operators will swap failing birds faster and accept higher attrition as the cost of doing business under a thinner shield. Climate coupling stays the slow burn. Expect more frequent winters where particle precipitation dents ozone over the poles, adding a small shove to circulation just when seasonal forecasts balance on edges. National weather services won't issue space weather winter advisories, but their models will ingest auroral energy inputs more consistently. The payoff is better odds on blocking patterns and polar vortex behavior weeks out. Farmers and grid planners will use that guidance without caring which knob. Sea ice, QBO, or solar protons tilted the board that month. Wildcards ride shotgun on this timeline. A Carrington-class solar event could arrive tomorrow or in 50 years. If it hits in a weak field decade, it's a stress test we'll talk about for generations. Satellite swarms juggling dragon radiation, grids straining under continent-scale currents, auroras at surprising latitudes, comms patchy in bands we thought were safe. Volcanic aerosols tossed into the stratosphere at the wrong time could compound circulation quirks, already nudged by space weather, turning a marginal flood season into a costly one. The uncomfortable truth is the human timeline. Soon enough to matter, late enough to procrastinate. Politicians prefer budgets that pay off before elections. Engineers prefer upgrades before failures. The phase we're in rewards the second group. Over the next 30 years, we choose margins. Thicker copper, smarter relays, sturdier satellites, better forecasts. The inner core's rhythm won't ask our permission. We set the schedule for how gracefully we ride it. The playbook, how we harden civilization. Enough doom. Here's how we buy margin while the shield wobbles. Boring work that pays every day it doesn't make the news. Start with the grid. You can't stop geomagnetically induced currents, but you can blunt them. Series capacitors break the DC-like path those currents love, turning long lines into shorter electrical segments. Neutral blocking devices on transformer grounds add one-way gates, letting lightning protection do its job while choking slow jigs. Operators upgrade transformer cores with better steel and more thermal headroom, add fiber Bragg grading sensors to watch heat rise in real time, and install GIC meters at substation neutrals. Deploy during storms, postpone planned outages, pre-stage reactive reserves, rebalance flows away from long east-west corridors, and lower trip thresholds on devices known to saturate early. Simple, deliberate moves keep small problems from becoming cascades. Transmission planning bakes space weather into models. Utilities layer magnetotelluric maps, how their geology conducts currents, on top of line routes, then simulate worst-case storms to find hotspots.
Where rock conducts too well, they throttle exposure with added series compensation or redispatch plans. Regulators can help by mandating GIC monitoring, funding neutral blockers on key transformers, and requiring annual storm drills the way they require cyber tests. It's compliance that buys light and heat. Satellites need a different toolkit. Start at the chip level. Radiation-hardened parts where it counts, triple modular redundancy for logic that can't fail, and aggressive error-correcting memory for everything else. Add watchdog timers that yank processors out of lockups without human intervention. Make safe mode logic SAA aware so payloads sleep through the worst passes on purpose, not by surprise. Put dosimeters on board and let autonomy throttle operations when the environment spikes rather than trusting distant forecasts. For fleets, distribute risk. Avoid synchronized SAA crossings for identical satellites. Diversify inclinations when mission design allows, and build in maneuver margins for drag seasons during solar maxima. The contract line that matters: specify storm mode and test it like you test propulsion. Ground segments harden too. Schedule critical uploads outside anomaly windows. Cache redundant command loads on the bird. Reserve extra ground stations during storms, so you're not waiting a full orbit to recover from a safe mode. Mission control rehearses lost in SAA drills until switching to dark mode settings is muscle memory. Insurance underwriters will ask for these checklists. Give them a thicker one than they expect, and your premium tells you if you missed a step. Aviation adapts with data and discipline. Equip fleets with real-time radiation monitors on long-haul aircraft and feed those numbers to dispatch. When proton events spike, dose-based thresholds trigger route changes automatically, not after debate. HF radio blackouts get contingency procedures that crews practice every 6 months. Handoffs to SATCOM, reroute protocols, and fuel reserves match to the longer legs. Airlines integrate space weather layers, auroral oval position, polar cap absorption, SAA extent, right into their route planners alongside jet streams and turbulence. Regulators can codify dose tracking for crews and set clear guidance on maximum exposure windows per quarter. No drama, just occupational safety done right. Pipelines and subsea cables tighten corrosion control. Install JIC IC sensors along long lines and program cathodic protection systems to ride through storm-driven swings without flipping polarity. Schedule inspection digs informed by GIC exposure history, not just mileage. At cable landings and long-haul terrestrial backbones, add surge protection tailored to slow geomagnetic swings as well as fast lightning spikes. Network operators model dual failures, grid plus cable, and pre-planned traffic reroutes, so a storm is an inconvenience, not a headline. Forecasting is our early warning, so we fund it like weather. Put more eyes upstream. L1 monitors that read the solar wind and IMF orientation, a sentinel at L5 to see Earth-directed CMEs sideways, and a dense ground magnetometer network across vulnerable geologies. Assimilate it all into models that spit out grid-relevant indices, local geoelectric fields, not just KP. For aviation, couple particle precipitation forecasts into dose models and HF-COM availability maps. For satellites, broadcast drag forecasts with confidence intervals so operators can schedule burns and do public alerting without theatrics. Clear, tiered advisories that tell the right people to act while the rest carry on. Research priorities align with the engine. Invest in seismic arrays and waveform inversion to keep tracking the inner core's rhythm. Expand secular variation mapping with satellites and observatories so flux patch drift is caught.
Early. Build better core, mantle coupling models that link torque changes to surface signatures. In the atmosphere, keep tightening the chain from particle precipitation to ozone to circulation, so seasonal forecasts can weight the space weather knob correctly. Standards stitch this together. Grid codes require GIC design cases. Satellite procurement specifies SAA-aware autonomy. Airlines adopt dose thresholds and codified detour triggers. Pipelines log and report GIC exposure. Insurers price to resilience, rewarding design that anticipates weak field decades rather than assuming yesterday's averages. Here's the quiet payoff. When the next storm hits on a thin field day, lights flicker but stay on. Satellites duck and recover. Flights detour without drama, and the news cycle moves on. That looks like nothing happened. It's everything. The inner core is weird biology. Snow, superionic states, and anisotropy. We've been talking like the inner core is a smooth steel bearing. It isn't. Down there, solid acts more like a personality than a phase of matter, and that personality changes how torque gets transmitted and how the dynamo breathes. Here's a micro story from the lab. A graduate student leans over a diamond anvil cell, lasers heating a hair-thin iron sample to thousands of kelvins, while pressure climbs to millions of atmospheres.
The diffraction pattern on her screen flickers, then stabilizes into a phase nobody saw at room conditions. The numbers imply ions are moving inside a crystal cage. It's not a direct sample of the core, but it's a believable stand-in. She emails the modeling team down the hall. 2 months later, their simulation shows the same phase boosting conductivity and favoring alignment under a modest magnetic field. The seismology group, reading the newest doublets, flags a fresh anisotropy tweak. The pieces don't prove each other, they rhyme. Start with the snow, not flakes you could catch. Think metallic crystals freezing out of the liquid outer core at the top of the inner core, then settling downward as a slurry. Seismologists call it a mush or snow zone, a layer where partly crystallized iron and light elements jostle like sleet in a lava lamp. That mush scatters seismic waves and tweaks their speeds, which shows up in those weird path-dependent delays we measure. For coupling, it matters, because a slick, granular layer can slip differently than a clean, solid surface. If the slurry thickens as heat flow patterns change, the magnetic clutch we talked about transmits torque with a little lag and a little extra damping. That's one way a deep pendulum loses amplitude without anyone flipping a switch. Now the superyonic twist. Under the pressure and temperature at Earth's center, iron doesn't just sit in a neat lattice with the rigidity we teach in school. Recent computational studies and high-pressure experiments suggest a phase where iron atoms lock into a crystal framework, while certain light elements, maybe hydrogen, carbon, or oxygen, move through that framework like a liquid. That's superyonic. Picture a rigid cage with ions slipping along the bars. The electrical conductivity in such a state can be extreme, which changes how magnetic fields thread and tug the inner core. A better conductor means stronger electromagnetic grip for the same flow changes outside. But a framework that lets light elements wander can also relieve stress and reorient crystals over time. In short, the clutch might grab harder, while the gear teeth quietly rearrange. Here's where anisotropy enters the scene. Seismic waves travel faster along the inner core's polar axis than along its equator, a sign that iron crystals align preferentially. That alignment isn't fixed. As new solid iron freezes onto the inner core's surface, it can inherit the local stress and magnetic environment, which slowly rotates the crystal grain over decades to centuries. If the inner core starts to lag, the stress field adjusts and the preferred orientation can drift, changing the anisotropy pattern we sense. That's a feedback. Rotation changes texture. Texture changes how waves read rotation. Rotation adjusts again. It's why those millisecond drifts aren't just clocks, they're X-rays of a living structure. Meanwhile, the inner core surface is not a perfect sphere. It's lumpy, kilometers of topography stitched by uneven growth and melting. Fluid shears across those bumps, adding viscous drag here, pressure torques there. In a snow-lined region, the bumps can be cushioned. In a bare patch, the fluid bites. That patchwork creates microcouplings that vary with longitude, tying inner core motion to the mantle's big features overhead through the flow that skirts between them. When we see flux patches drifting beneath Africa and South America, we're likely seeing the outer core react to a boundary that's anything but uniform. What nobody knew, until the waveform catalog got long enough, was whether these exotic states just decorated.
The story or drove it? The answer is probably both. Superyonic behavior boosts conductivity and alters magnetic friction. Snow layers tune slip. Anisotropy flips our seismology into a sensitive microphone. Put them together, and the stop we headline is more like a gear change. The drivetrain didn't stall. The transmission shifted under load. Another detail that matters: the inner core's growth isn't uniform. If more iron solidifies on one hemisphere than the other, you build a mass imbalance. Gravity tries to center that bulge. Magnetic stresses try to pin orientations. Outer core flow carves around the asymmetry. Some studies suggest an eastern hemisphere growth preference over long spans. If that's true, torque transmission isn't just time variable, it's lopsided. The slowdown we see could be partly the inner core settling into a slightly new stance, like a dancer shifting weight before turning. Impact, back at the surface. These microphysics don't automatically spell disaster, but they do make the engine more sensitive to modest changes in heat flow and flow geometry. A thicker snow zone here, a superyonic patch there, a nudge in anisotropy across a key longitude, and the outer core's convection lanes reorganize. The magnetic field above responds with driftier lobes, a slackening dipole, and a South Atlantic anomaly that refuses to behave. None of it requires a flip. All of it benefits from noticing early. It's like your ice cube growing spikes in a lava lamp. Still cold at heart, still solid, but full of motion that changes how it interacts with the fluid around it. When the inner core's biology gets weird, the clutch we rely on changes character.
That's why the waveform pivot mattered. It wasn't just a new beat, it was a hint that the instrument itself had retuned. The people in the lab, doubt, debate, and the millisecond wars. Unknown to most of us, the front line of this story isn't a volcano rim or a satellite control room. It's a dim office with a messy whiteboard and coffee rings on printouts. The scientists living with this problem don't speak in viral headlines. They argue over tenths of a second, over which filter belongs on which waveform, over whether a wiggle is physics or an artifact. Note on attribution. In 2023, Song and Yang's Nature Geoscience paper framed the slowdown as part of a multi-decade oscillation. In 2024, a Nature study extended doublet analyses through 2023 and quantified the recent backtracking. Different tools, converging direction, exactly what you want when the instrument is the planet. Here are the stakes they feel but rarely say. If they call it wrong, if they oversell a slowdown or miss a pivot, policy gets skewed, budgets swing, and the public tunes out next time. But if they're too cautious, operators don't harden grids and fleets until a storm forces the lesson. That tension hums beneath every email, every reviewer's note, every press call. Action starts with a data room. On one wall, stacks of South-sandwiched doublets, years apart, paths nearly identical. On another, array recordings from Yellowknife and Eilson, needle-fine beams cutting noise to tease out PK-IKP arrivals. Someone circles a 0.02-second drift. Someone else asks whether the instrument response was updated in 2015. A graduate student reruns a stack with a different cross-correlation window, and the number shifts by a hair. A hair matters. This is the millisecond war. Alignment strategies, signal-to-noise thresholds, and the eternal fight against confirmation bias. Meanwhile, across the world, another group prefers normal modes, the free ringing of the whole Earth after giant quakes. Their math is brutal, their confidence high. They publish a rotation estimate that grazes the others but doesn't match. In a hallway talk at a conference, an older seismologist smiles and says, "Good, if two methods agree too neatly, we should worry." They aren't being smug, they've seen pretty numbers fool smart people. What nobody outside the room sees is the argument choreography. Drafts circulate with surgical comments. Check array calibration drift 2003 to 2008. Try removing SSI event pair 1997 of 201. Rupture complexity suspected. Sensitivity test. What if anisotropy change mimics rotation? A co-author pushes to call it reversal. Another says backtracking is more honest. They settle on language that won't explode on a headline, then watch a headline explode anyway. Here's a micro story. A postdoc schedules a press briefing because the journal requires outreach. She rehearses relative to the mantle 5 times, not a literal stop 10 times. The first question from a reporter, "So the core stopped spinning?" She breathes, says no, explains the lead lag. An hour later, a site post, Earth's heart halts. Her inbox fills with panic and snark. That night, she goes back to the array because the only antidote to noise is another stack that holds up. But there was one problem. Science can't PR away. The data are inherently sparse. We don't get to choose when earthquakes repeat on clean paths. We don't get to put seismometers under the South Atlantic. So the community leans on open repositories and long friendships. Someone in Japan shares a catalog of doublets they curated for years. A European lab releases array beamforming code. An American team posts their waveform selection criteria so critics can reproduce the drift. Or fail to, honestly. The disagreements get sharper and more useful when everyone is arguing over the same raw material. Meanwhile, on the magnetic side, geophysicists who live in spherical harmonics watch the seismology fight with empathy and caution. Their maps of flux patches and secular variation come with their own uncertainties. Satellite offsets, crustal contamination, model choices. In a joint workshop, someone draws a line from an inner core torque change to a westward drift acceleration. A hand goes up. Correlation isn't causation. Another hand. True, but if both are responding to the same deep reorganization, the risk argument stands. The room nods. They're not chasing a smoking gun so much as converging lines. Careers ride on this. A young researcher with a bold oscillation period risks being the slowdown person forever. A senior figure who preached steady super rotation risks a mea culpa. Most split the difference. We were right about the mechanism, the cadence is different. That's not spin, it's how science moves when the instrument is the whole planet and the sample size is small. Open science, helps, and hurts. Preprints get attention before peer review sands down rough edges. That speed lets satellite operators update risk models faster. It also lets misinterpretations sprint ahead. Some labs now pair releases with technical notes written for engineers. No metaphors, just ranges and caveats. The notes don't go viral. They land where it counts, in control rooms. Here's another micro story. A swarm team lead gets an embargoed update. SAA sub-minimum intensities dipped another few micro-teslas this quarter. Hotspots are separating. He forwards it with a single line to a private ops channel. Shift maintenance windows off 13 to 1600 hours universal time coordinated passes. 30 people's calendars change. No tweet required. Healthy uncertainty is their shield. In meetings you hear, "We don't know yet," said without apology. Someone lays out 3 scenarios: long oscillation, shorter cycle, or quasi-steady with episodic jolts. Each comes with testable predictions. They assign homework. If it's 70 years, the drift sign should flip again by X. If 30, we should see Y in the next SSI sequence. The calendar goes on the wall next to the coffee stains. This was the moment everything changed for them. Not a single paper, but a rhythm in the updates. New doublets added through 2023 still pointed to backtracking. Flux patch models kept showing the same migrations. Operators kept sending quiet notes about rising SEU counts over the SAA. The chorus got louder, not because any one voice shouted, but because more instruments joined. That's how scientists get convinced, not by drama, by accumulation. In the end, these people live with not knowing as a craft. They don't chase certainty, they narrow the possibilities. They remind each other that precision isn't always accuracy, that millisecond shifts can carry planetary meaning, and that the right response to a wobbling shield is not fear, but preparation. Their war isn't against each other, it's against complacency. What this means for us: risk without drama, urgency without panic. Take a breath. The inner core changing rhythm isn't a doomsday bell, it's a diagnostic tone. The line we can't cross is hype that outruns the data. We stick to verified trends: a measurable deceleration relative to the mantle, a South Atlantic anomaly that's spreading and splitting, a centuries-long dipole decline, and credible pathways for tech and atmosphere to feel the strain. That's enough to act without inventing monsters. At the personal level, this shows up as inconvenience with teeth. Traveling? Expect occasional polar route detours during solar proton events, plus patchy high-frequency radio on the worst days. Your devices won't melt, but GPS can wobble slightly during storm peaks, so navigation apps lean harder on corrections and cell networks. Satellite-dependent services, imagery, comms, timing will schedule routine maintenance around anomaly windows. Outages will be shorter and more planned if operators stay ahead of the curve. Awareness beats anxiety. If space weather alerts pop up, think strong storm day. You don't cancel life. You know flights may reroute, auroras might show up far south, and satellite services could stutter. If you work outdoors at high latitudes or fly frequently, your employer should track dose and follow standard limits. If you're a ham radio fan, you already speak ionosphere. On storm days, your bands will tell you before we do. Societal level action is
dull by design. Budget shift toward grid hardening. Series capacitors on long east-west lines. Neutral blocking on vulnerable transformers. GIC monitors as standard kit. Regulators write storm drills into compliance and require utilities to share real-time geomagnetic data. Satellite manufacturers spec more error-correcting memory, SAA-aware autonomy, and onboard dosimeters. Insurers reward missions that can storm mode without human hands. Aviation authorities standardize dose tracking and polar reroute triggers, so every airline plays the same safe game. International coordination keeps the noise down. Space weather forecasting is a global commons. L1 monitors, L5 views, magnetometer arrays across continents. Shared indices that translate solar wind into local geoelectric fields help grid operators act precisely rather than broadly. Data openness also tempers overreaction. When everyone sees the same curve, nobody needs to shout. Here are the honest unknowns. We don't know the exact cadence of the inner core's oscillation beyond decades, or how strongly that cadence modulates flux patches at the top of the core. We don't know whether the current weak field phase will plateau
worsen or recover on human timescales. We don't know the precise strength of climate coupling. The space weather signal is real in the upper atmosphere, modest at the surface, and tangled with larger drivers. And we don't have a deterministic trigger for reversals versus excursions. Those choices belong to a chaotic engine. So we bet on resilience rather than prophecy. Harden the parts that fail first. Long conductors, sensitive chips, low-orbit satellites. Improve forecasts that buy hours to days of lead time. Solar wind arrival, particle precipitation, drag. Write standards that make thin feel decades. A design environment, not an afterthought. Then practice. Run black sky drills for grids. Run lost comms drills for airlines. Run safe mode recovery drills for mission control. The day it matters, muscle memory outruns adrenaline. Payoff, stated plainly, we're not helpless. The shield is wobbly, and we can brace. Most of the fixes pay back even if the field quiets later. Transformers run cooler, satellites last longer, forecasts get smarter. The fear story sells views. The preparation story pays bills. Watch these tells. If SAA subminima continue to deepen and separate, satellite ops will tighten schedules again. If flux lobe drift speeds up, grid planners will lower storm thresholds. If seismic doublets show the inner core's lag easing, the torque balance might be bending back. If not, we stay on the cautious path. Either way, we're steering, not waiting. The planet's heart didn't stop. It changed rhythm, and that new beat sets how hard the next solar punches land on our tech and skies. Here's the part that matters for you. On storm days, your flight may reroute, your GPS may wobble for minutes, and the satellite services you depend on may briefly stutter. That's not panic fuel. That's a prompt to harden what we own and run the drills we control. If you want the next chapter, an on-the-ground play-by-play of a real solar storm, stress testing our thinner shield, from the first CME alert to satellite drag spikes, SEU counts, HFCOM blackouts, and grid operators shifting into storm mode, watch the follow-up linked here. Subscribe for more freaky science that trades jump scares for clear steps, and share this with the one engineer in your group who quietly keeps the lights on. Their work is why most people will never notice the wobble.